Base Excitation Application by Patrick Beal and Brian Bashir. The transistor industry has been plagued by the inability to effectively remove unwanted silicon dust particulates that adhere to the wafer during the manufacturing process. This results in unreliable circuit performance, defects, and if caught, the disposal of thousands of transistors. To remove the particulates, many have tried to use brush cleaning techniques. Others have utilized non-contact lasers. Some have even gone as far as to use atomic force microscopes. However, these methods are often expensive, inefficient, and can damage the substrate. Our solution?
Cause the players gonna play, and the haters gonna hate, baby. I'm just gonna shake it off.
Shake off the particulates. Base excitation models the behavior of a vibration isolation system. In such a model, the base of a spring is given some prescribed input motion, causing a mass to vibrate. While a car is driving along a bumpy road, its suspension system can be modeled as a vibration isolation system. Even the structure of a building during an earthquake could be modeled as one. Or even substrate particulate interactions. To quickly review the dynamics behind a base excitation problem, we turn to a simple example. The transmitted force from the spring and damper to the mass is shown here as F sub t. Now, setting the transmitted force equal to the mass times its acceleration leads to the governing equation of motion. And after using a Laplace transformation, the following transfer function can be obtained. This transfer function is called the displacement transmissibility. Taking the Laplace transformation of the original transmitted force equation and then substituting for x of s in the above equation and dividing by the spring constant k leads to the second desired ratio, the force transmissibility. If the frequency domain is required, then substituting j omega for s in the previous equations leads to both transmissibilities in the frequency domain. And finally, both displacement and force transmissibilities can be expressed as magnitudes. In order to start this problem, we first examined the real-world situation of particulates on a substrate, shown on the left, and modeled it as particulates distributed across a pin beam attached by springs. By oscillating the base, the particulates will continuously contact the substrate. In order to simplify the calculations regarding this contact problem, we decided to attach the particulates to the substrate by means of springs. We broke this initial model into two, one of which is a discrete system and the other a continuous system. In order to further simplify, we've modeled a single particulate. In the discrete case, the substrate is displaced by a function y of t. The particulate, as shown on the right, experiences both an adhesive force and the spring force. By manipulating the function y of t, we hope to determine an appropriate base excitation to distance the particulate from the substrate. Once separated, the particulate will be removed from the substrate by means of water or airflow. The continuous system is a bit more complex. Here, the substrate with a mass of big M will be broken up into n number of segments, each with a length of z. In this case, the equation of motion focuses on the substrate segment rather than the particulate. Given more time and resources, we hope to further develop the continuous system model. However, for now we are focusing our efforts on simulating the system in the discrete case using MATLAB. We will have the necessary equipment in early January to complete the initial experimentations using piezoelectric actuators to excite the base and silica spheres as particulates on a silicon wafer. Thank you.